Have you ever looked closely at your phone screen, or maybe at a bright LED light, and wondered, how does it produce such sharp, specific colors? Well, it's not some magic beta, it's pure chemistry. And the secret ingredient is a very special family of elements that many students find confusing.
All right, so let's begin. Today, we are going to talk about the lanthanoids. Now, you remember the periodic table, right? Those two rows that are kept separately at the bottom? Yes, that is the F block, and that is where you will find them.
So you might be asking, sir, why should we study this particular group of elements? And that is a very good question. The answer is because they are absolutely crucial for so many of our modern high-tech things. From the phosphors lighting up our screens to powerful magnets, understanding lanthanoids is key to understanding the world around us.
So what is the whole story of these elements? Now listen carefully. This is the single most important idea you must grasp. If you understand this one thing, the whole topic becomes easy. Unlike the transition metals, which have very different chemical personalities, the lanthanoids are all remarkably similar to each other. You can think of them as identical twins. Just think about it. The transition metals, they're like different characters in a story. You have iron, you have copper, you have manganese, all with different properties, different oxidation states. But the lanthanoids, they are all so similar. Chemically, it's almost impossible to tell them apart. So the big question is, of course, why? Why are they so uniform? The reason is hidden deep inside their atomic structure. Let's call it the story of the shielded electron. First, we must define one very important concept, and that is shielding. What is it? Simple. The electrons in the inner shells, they form a sort of screen. They block the outer electrons from feeling the full positive charge of the nucleus. Please remember this. This one word, shielding, is the entire key to understanding the lanthanoids. Now look at this atomic structure. This is where it gets very interesting. For the lanthanoids, as we go across the periodic table, we are adding electrons to the 4f orbitals. But where are these 4f orbitals? They are not on the outside, no. They are buried deep inside the atom, and the outer electrons, the 5d and 6s electrons, are shielding them completely. This is the main point. This explains everything. To make this even simpler, let's use a nice mental picture. Imagine each lanthanoid item is a box, a special kind of box, one that has a hidden drawer inside. Okay, so the outside of this box is what interacts with the world. This is like the outer electrons, which are lost very easily. And because they are lost, every single lanthanoid shows a very stable +3 oxidation state. So from the outside, all these boxes look and behave in exactly the same way. But what about that hidden drawer? Inside that drawer, things are changing. One element has one 4f electron, the next has 2, and so on. But because this drawer is hidden, it's locked away. It cannot be accessed. So whatever is inside it, it does not affect the chemical behavior of the box at all. These 4f electrons are chemically, well, irrelevant. And this brings us to a very common confusion. Logically, you might think, sir, transition metals fill d orbitals and show many oxidation states. Lanthanoids are filling f orbitals, so shouldn't they also show many oxidation states? It's a very logical question. But the answer is no. And why? Because those 4f electrons are locked away. They are so well shielded that removing them needs a huge amount of energy. It's just not practical. So the atom just gives up its easy-to-remove outer electrons, settles into the +3 state, and that's it. The f electrons just sit inside, not taking part in any bonding. Now, you can imagine this extreme similarity, it created a big problem in the real world. For the chemists who first discovered these elements, it was a total nightmare. For many years, chemists really struggled to separate them. Imagine, they would find a new mineral, but they could not tell if it was one new element or a mixture of 5 different lanthanoids. Because they all behave identically, all the normal chemistry methods for separation, they just did not work. So why was it so difficult? Let's say you are in the lab and you have a solution with a mixture of lanthanoids. You add a chemical hoping to precipitate only one of them. But what happens? Poof! All of them precipitate out together. Why? Because their compounds, their hydroxides, their sulfates, their phosphates, all have almost the exact same solubility. It was a very frustrating problem for chemists. But now, here comes the interesting twist. The very same property that was a nightmare for chemists, this shielded nature of the f electrons, This has become their biggest strength in today's technology. Let's go back to our first question about phone screens. That technology uses special materials called phosphors. So what is a phosphor? It is simply a material that can absorb high-energy light, like UV light, and then give it out again as lower-energy visible light that we can actually see. And this is where lanthanoids are perfect. Literally, they shine. Remember those hidden 4F electrons? Because they are so protected from the outside world, their energy levels are very sharp and very specific. This allows for electron jumps between these F orbitals, which produce an incredibly pure, sharp color of light. For example, use europium, you get a beautiful sharp red. Use terbium, you get a sharp green. This property is perfect for making the individual pixels in your TV and phone screen. Okay, so that was a quick tour of the world of lanthanoids. Now, let us quickly summarize the most important points you need to remember for your exam.
So please pay attention. The main points are these. Number 1, the core idea. Their chemistry is so similar because their 4F electrons are buried deep inside and are shielded. Number 2, the mental picture. Just remember the identical twins or the box with the hidden drawer. And number 3, the key example. Remember their use in our screens as phosphors because of those special F to F electron transitions.
If you can just remember these 3 things, the core idea, one simple mental picture, and one application, I promise you this topic, the lanthanoids, will feel much, much easier in your exam. All the best.